Right. The previous lesson we started on the study pack 19A, which is chemistry of the carboxylic acids and derivatives. I'm supposed to complete this study pack today and complete the IR spectroscopy as well. We started this last week, and halfway through, we completed it. I explained about the dimerization reaction, dimerization and hydrolysis of the nitriles to form the carboxylic acids. The acid hydrolysis or the alkali hydrolysis, of course, gives sodium salt of carboxylic acid, and the acid hydrolysis of the cyanide gives the carboxylic acid itself. So we discuss about the boiling and melting points, general formula, and homologous series, physical states, how the carboxylic acids can be made by the oxidation of primary alcohols, oxidation of aldehydes. And I also explained about the dimerization, right? How two carboxylic acids can form two hydrogen bonds and act as one molecule. There where we stopped. Am I right? Or did I complete? Did I do more reactions? Did I do on this question 5? Okay, we have to start from question 5, right? Let's look into the reactions of the carboxylic acids. The first reaction is a reaction with the reactive metals to form salt and hydrogen gas. Now, carboxylic acids react with the reactive metals such as sodium, group 1 metals, or even group 2 like magnesium, calcium. It produces the it produces a salt and the hydrogen gas. So let's take this common carboxylic acid reacting with sodium. Get the sodium salt of carboxylic acid and hydrogen gas. If it is a group 2 metal like calcium or magnesium, look at the sodium salt of carboxylic acid and hydrogen gases. Like any other acid reacting with metal reaction. Of course, with sodium, it's quite a dangerous reaction. We know sodium with water itself is violent, so with acids, even weak acids, is quite dangerous. But still, it reacts. But in laboratory, we don't do these reactions. And if you want to demonstrate, we have to do under extremely highly controlled conditions. But group 1, like lithium, is very safe, and group 2, it reacts safely, right? So carboxylic acids will react with the metals to form the salt and the hydrogen gas. Please copy the reaction. The next is a reaction of the carboxylic acids with alkali to form salt and water. Right, like the reaction of carboxylic acids with group 1 metals, it does react with the alkalis as well, like, for example, sodium hydroxide, like any other acid alkali reaction that produces salt and water. And like any other neutralization reaction. Any other acid alkali neutralization reaction. This produces salt and water. Let's copy the reaction. And for the reaction of sodium carbonate and sodium bicarbonate, sodium carbonates and sodium bicarbonates does react with carboxylic acid. That is a specific reaction of sodium carbonates and sodium bicarbonates with the carboxylic acids. In fact, is used as a test for the carboxylic acids, test for organic acids, carboxylic acids. So any carboxylic acid will react with sodium carbonate, like any other acid reacting with sodium carbonate, that will produce sodium salt of carboxylic acid, carbon dioxide gas, and water, right? Carbon dioxide gas and water is produced. And if you take, for example, group 2 carbonate, salt, carbon dioxide plus water, the same reaction is observed with bicarbonate. This is, I say, sodium carbonate and sodium bicarbonate. So I'm going to write the second reaction as the bicarbonate. Same products. Sodium hydrogen carbonate. It gives salt, carbon dioxide plus water. So this specific reaction can be used as a test for the organic acids. Organic acids, the weak acids, the carboxylic acids. Please copy the reactions. Let's see how the carboxylic acids can be reduced with strong reducing agents. As you know, the primary alcohols undergo oxidation to produce carboxylic acids, right? When you add oxidizing agents such as potassium permanganate or potassium dichromate acidified with the sulfuric acid, if you heat under reflux, the primary alcohols gives the carboxylic acids. Likewise, the carboxylic acids can be reduced. It can be reduced to give the primary alcohol. Now, reduction of carboxylic acids can be done by strong reducing agents such as lithium aluminium hydride in dry ether conditions, because we know we discussed in the last lesson lithium aluminium hydride is highly sensitive to water. Water destroys lithium aluminium hydride, so therefore whenever you use lithium aluminium hydride you have to use extremely anhydrous conditions. So but we cannot use sodium borohydrate because sodium borohydrate is a selective reducing agent, can be used to reduce only aldehydes and ketones, but lithium aluminium hydride can be used to reduce any substance with a carbonyl group. So it can be aldehyde, it can be ketone, it can be amide, acid chlorides or carboxylic acids, esters, anything can be reduced by lithium aluminium hydride. So what happens when you reduce carboxylic acids? You get the corresponding primary alcohol. This is anhydrous lithium aluminium hydride in dry ether. Get R, the carbonyl group turns to a CH2. The C double bond O turns to CH2. So this is a primary alcohol. So like primary alcohol can be oxidized to carboxylic acid in the presence of strong oxidizing agents, carboxylic acids can be reduced to primary alcohols in the presence of lithium aluminium hydride, meaning strong reducing agents. So lithium aluminium hydride, again, we know, I explained this last week, it has aluminium hydride. The aluminium hydride releases the hydride ions. Unlike the hydrogen gas which releases H plus ions, the hydride ions is a powerful nucleophile, so that attacks the plus delta carbon over here and reduces the carbonyl group. So therefore, we cannot use lithium aluminium hydride to reduce the alkenes, carbon-carbon double bonds cannot be reduced effectively with lithium aluminium hydride, because lithium aluminium hydride releases the hydride ion, not the hydrogen ions. Please copy the reaction. trying to draw a molecule here. Say a molecule which contains, I think I gave this last week also. It contains a carbon-carbon double bond, and you have a ketone and a carboxylic acid. Right, you have three groups here: carboxylic, ketone, and at last we'll draw the aldehyde. Let me just draw this smaller. So you have aldehyde group, and you got carbon-carbon double bond, got the carbonate group and a carboxylic acid, and then got three reducing agents. One is hydrogen nickel catalyst at 300 degrees Celsius. Let's see what happens there. And then you have lithium aluminium hydride in dry ether, and you got the sodium borohydrate. I'll give you a minute. Write the products. Write the products. And let's check the answers. Now, hydrogen nickel catalyst reduces a carbon-carbon double bond. So you get CH2, two hydrogens added. Nothing happens to the carbonyl groups or the carbonyl compounds because hydrogen nickel catalyst releases H plus ions. As for lithium aluminium hydride in dry ether conditions, you can reduce everything, any carbonyl group. So this turns to OH, CHH, but not the double bond. Ketones turns to secondary alcohol. Aldehyde turns to primary alcohol. The carboxylic end also turns to primary alcohol. And sodium borohydrate, only the aldehyde and the ketone is reduced. Nothing happens to the carboxylic end because sodium borohydrate is a selective reducing agent. Nothing happens to the carbon-carbon double bond. Nothing happens to the carbonyl group of the carboxylic acid. Only aldehydes can be reduced. Clear? Right. Let's look into the final reaction, which is the esterification reaction of the carboxylic acid. Now, esters are sweet-smelling compounds. They have sweet, fruity smell, which is formed. Ester is formed as a result of the reaction between carboxylic acids and alcohols, or acid chloride. Acid chloride of the carboxylic acids also can be used to increase the rate of the reaction or yield of the reaction. Let's see how ethanoic acid reacts to form ester with ethanol. Now, when you draw the ester, it's easy for us to draw the structure of the ester if you draw the structures so as the two OH groups face each other, right? So this particular reaction is catalyzed by concentrated sulfuric acid. We need to slightly warm the reaction mixture, and what happens is that a water molecule will be lost. Now, it's very important to know which atom gives the OH and which one gives the H in the esterification reaction. So remember, the carboxylic acid, the acid doesn't give the H here. The acid gives the OH, and the alcohol gives the H. The reason is explained in the mechanism. This is addition reaction followed by elimination. In short, we call this reaction as a condensation reaction. As I mentioned last week, a reaction of 2,4-dinitrophenylhydrazine with the carbonyl compounds is also example for a condensation reaction. That is because addition is followed by elimination. So likewise, this reaction, you can see the lone pair of the oxygen attacks this plus delta carbon. So that's addition reaction followed by elimination of a water molecule. In short, this type of reaction is referred to as a condensation reaction. So you get this ester. What you do is you form a bond with this oxygen of the alcohol. So this ester is named as ethyl ethanoate. When you name the esters, as we discussed in the very first class of the organic chemistry, you name the species, the group which comes next to oxygen first, right? You name this group which comes next to oxygen first, that is the ethyl group, and then you name the rest of the molecule. So it's ethyl, and that substituent does not have any number. That's a no number substituent, and then you name the rest of it, right? Ethyl ethanoate, right? So now this, you might want to know why it's so important that to know which carbon gives, which molecule gives H, which molecule gives the OH. Now suppose if I remove like this, if I remove the H and OH, say OH from the alcohol and the H from the carboxylic, if I remove the water molecule that way, still you get the same product, CH3, C bond O, C2H5. But that is wrong, because so you get caught if the oxygens are labeled. If your oxygen is labeled, right? Say for example, I call this oxygen, say I will label this as O18 and O16. This is O18 and this is O16, right? 18 and 16. So in that case, 16 should come to the ester, 18 should go to the water. So you get caught if either oxygen is labeled, or sometimes they mark the oxygen with asterisks, then you will know the answer is right or wrong. You should always remember the alcohol gives the H and the hydrogen gives, the carboxylic acid gives the OH, right? So this is ethyl ethanoate. In fact, this is a pineapple flavor. Pineapple flavor. So these are artificial flavors, right? Likewise, different flavors you can make, all these essences like vanilla essence, banana, or whatever essences you have, like food essences, food flavorings, they all are, you don't think it's natural, they're all artificial, and most of them are carcinogen. Most of them are cancer causing. That's very dangerous because, we are very used to these flavors, artificial flavors. Even to the small children nowadays, you see cancer is so common because they always drink this flavored milk. Do you think they put real vanilla for the flavored milk? In that case, a packet of vanilla milk will cost about 1,000, 2,000 rupees. Right? How can they give a packet of milk for about less than 50 rupees? Because they're all artificial esters. They're all artificial esters. Long term, they have very bad effect on the health and even the perfumes we use. And for the perfumes, they use aromatic compounds. Aromatic compounds are benzene rings, benzene molecules. Benzene compounds are known as aromatic compounds. They are phenyl compounds. We were studying in A2 about benzene molecules and about chemistry of benzene. So most of the perfumes they use is aromatic compounds. This you have to know, because it's very important that you incorporate your chemistry to your life, because not just to pass the exam. Of course, they will not ask these things in the exam, but what's the use of, education if your education cannot save your life, right? At the end of the day, right? So these things you remember. Even the perfumes, right? It's most of the artificial perfumes are synthetic perfumes are carcinogen. They are cancer causing. Usually, you apply on the body, and whatever apply on the body externally, it's absorbed through the skin to the inside the body. So they're very dangerous. And of course, good old days we use natural, smells, natural extracts like essential oils. Still, those perfumes are available. They're quite expensive. And now, of course, they have derived a different, therapy known as aromatherapy using those. So actually, those are the real perfumes. Real perfume, if you use, you can get rid of most of your sickness. including arthritis or so many different types of even headaches, migraines, all can be cured by these perfumes itself.